So if you hopefully remember from today, we finished by talking about some rules of inference. So we had, for example, modus ponens, which was this first rule here. Basically, if you're writing a proof, and if you have already proven P, and you have also already proven that P implies Q, then you can easily just add Q to your proof. And you can say that I have proven Q. Now, we have a bunch of other rules. And generally speaking, these rules are basically the same as tautologies. So it's just a different way of writing tautologies that have some premises or hypotheses and some conclusion, right? So we have, for example, this one here, modus tollens, if I pronounce that correctly. And basically what it says is that if you have proven that P implies Q, and you have proven that Q doesn't hold, you have already proven that P doesn't hold. Which is the same as saying that if we just take the conjunction of all the premises, so P implies Q and not Q. This whole conjunction implies the conclusion, implies not P. And this whole formula is actually a tautology. So you can just create its truth table, and it will always evaluate to true. And because it always evaluates to true, we can basically write it in this format and use it as a rule in our proofs. Now, let's look at a bunch of other rules. Now, as I said before, at some point during this course, we will get to a system of proof where we show that modus ponens is the only rule that we need. So if you only have modus ponens, you can prove whatever you can prove with all of these other rules. So they're not going to give you any extra power, but they're nice. And you can use them in your proofs anyway. So here's a really brain-dead one. It says that if you have proven P and you have proven Q, you have also proven P and Q. Can you believe that? If you've proven P or Q, so you have proven that one of P or Q holds, and you have also proven that P is not the one that holds. So you have proven that Q is the one that holds, right? Now, this one is more interesting. It says that if you can prove that not P implies F, that has already proven P. So this is proof by contradiction. So if I want to prove that P holds, I can assume that not P holds and show that not P leads to a contradiction. Remember, F was our notation for contradiction, something that always evaluates to false. So if not P implies a falsehood, a contradiction, then P must definitely hold. Okay. Then we have a bunch of other things. So if you've proven P and Q, you've proven P. Of course, you've also proven Q. If you've proven P, you have proven P or Q, because P or Q is true whenever P is true. This is another one. So suppose that you have proven P and Q, and you have proven that P implies that Q implies R. So you can just open up these implications and you can say, I already have it. We have a bunch of other rules. And again, all of these rules are just different ways of writing tautologies. And you can either prove them using other rules. And again, as I said, modus ponens is enough to prove all of these. Or you can prove them by just creating a truth table and showing that all of them are actually tautologies when written in this implication form. So when you write them like this, that the conjunction of all the hypotheses give you the conclusion, imply the conclusion, this is a tautology. Okay. But let's actually do just one example of a proof. And I'm not going to do more than one example because I'm going to give you some reading material that has many examples. And also because this is not a very interesting logic. I want to extend the logic and add some other things so that we can do really interesting stuff. But let's say I want to do just one example. So this is a theorem that I want to prove. So assuming, let's see, we have three assumptions. P implies R. So this is the first assumption. And not P implies Q. This is the second assumption. and Q implies S. This is the third assumption. Prove that not R implies S. Okay. Now, one way to prove this would be to just do the truth table again. I had much more energy in the morning. I don't have enough energy to do it now. So you can prove it like that, but I don't want to prove it like that. I want to write a proof. And remember what our definition of a proof was. I'm just going to write a series of statements, and each one of the statements is either one of my premises, one of these three, or can be obtained by the previous statements using one of the rules, one of these many rules, whichever you want to use. Okay. So let's do this. Let's say I start my proof, and first I take my first premise, P implies R. Now, when you're writing proofs and also in the exam, you have to say where you're getting every part of the proof. So this one is just a premise. Okay. Now, what can I do to rewrite this? So another thing that I can do is, remember, I talked about this idea of equivalence. I said that if I have two equivalent formulas, or if I have two equivalent statements, I can always replace them with each other. You can think of that as another rule, okay? So if I want to add a rule of equivalence, I can add this. I can say that if P is equivalent to Q, and I have proven P, then I have proven Q. But again, this is a very silly rule. It's, of course, right. Okay. So the first thing I do, and this is very often done, is that I want to get R to the left side. So I find an equivalent statement to P implies R. And here's the thing, P implies R is actually equivalent to not R implies not P. Do you see why this is the case? So generally, this holds for any statement. It doesn't have to be this particular P and R. So if I have P implies R, again, just look at it as a promise. I'm promising that whenever P holds, R will also hold, right? But that's the same as promising that whenever R does not hold, it's because P also doesn't hold, right? So I'm promising, let's say P then R is this promise. I'm promising that if it's raining, then there are clouds in the sky. Okay, so P says it's raining, R says there are clouds in the sky. This one says if there are no clouds in the sky, then it's not raining. These two sentences are the same. Now, again, how do you formally prove that? Do the table. Okay, but this is one of the most common equivalences that we use in this course. Okay. So if I want to continue my proof, I can now add this one to my proof as well. So my proof is only this part, by the way. This is my proof. Everything else that I'm writing here are just my own notes. Okay. So I have not R implies not P. And I have this because of the rule of equivalence. Okay. And basically because of this, because P implies R is the same as not R implies not P. Okay. But now I have not P here, and I look at my premises and I see that I have a not P here as well. So maybe I can use this premise. So let's do that. Let's copy this premise into my proof. Not P implies, oops, there was no not there. Not P implies Q. Okay, so this was a premise. Now, what do I have? not R implies not P implies Q. Okay, which one of these rules can I apply? I can apply the syllogism rule. So it says that if P implies Q and Q implies R, then P implies R, right? Now I'm going to apply this rule. The difference is that instead of P, I have not R, but that's fine. I can just plug not R for P here, and instead of Q, I have not P, and instead of R, I have Q, okay? So if I do that, I get almost what I want, but not exactly. I get not R implies Q, right? This is the rule of syllogism. I don't remember how to spell that. Okay. This will be forever on YouTube that I don't know how to spell syllogism. Rule of syllogism, but I have to also say where I applied it to. So I can just add line numbers to my proof. So let's say this is line 1, this is line 2, this is line 3, this is line 4. So rule of syllogism applied to lines 2 and 3. Okay. So lines 2 and 3 will be the these parts, premises in my syllogism rule. And what I'm now adding to my proof is the conclusion of my syllogism. Okay. But this is not what I wanted, right? I wanted to say not R implies S, but what I have here is that not R implies Q. But thankfully, I have this extra assumption or premise that I have not used yet, which is that Q implies S. So let's use that one. So I write Q implies S. This is a premise. And then I can again apply the rule of syllogism. Not R implies Q, Q implies S, so not R implies S. Okay. This is 6. Not R implies S. The same rule. But this time applied to 4 and 5. Okay, great. This is a proof. Yes.
We have to memorize the rules in
No.
Excel.
No. This is just one example. And again, as I told you later in the course, we will see that we only need this rule. So we can derive all the other rules from this one, modus ponens is in it. So you have to memorize that if you have proven P and you have proven P then Q, then you have Q. Okay. Now, so this is what a formal proof looks like. Now, there are several things about this proof that are kind of different than all the other proofs that you have seen. One of the most important things is that it can be checked by a machine. So I can have an algorithm and I can just give it this proof. And as long as the algorithm understands my notation, as long as it understands how I'm writing these things, and as long as it has a list of rules, it can just automatically check that this is a correct proof. Okay. So this is very important for some parts of theoretical computer science, like the verification community and so on. But this is not usually how we write proofs ourselves, right? So as a human, I would actually explain all of these things, right? So, and in the exam, I would expect you to write these things in English instead of writing such a formal proof. But this is the formal mathematical definition of what a proof is. Okay? Great. So how would I actually write it as a human? I would say, well, I have the assumption that P implies R, and I know that that's equivalent to not R implies not P. And then I know that not R implies not P implies Q. So I can merge these two implications and say not R implies Q. So I will just explain this in human language instead of actually saying exactly this is the rule of syllogism. Okay. But now we have an example of a proof. Again, in the reading material, you will see many more examples of proofs. But let's go on and let's create a more expressive language for our logic. Let's create a language where I can talk about more things. Because right now, I have these atomic propositions, and I can just combine them in very few limited ways. I can do and, or, I can do a bunch of other things, but it's limited. So I want to do something much more interesting. I want to do quantifiers. Okay, so quantified formulas, or actually, let me start by defining predicates. What is a predicate? So a predicate is an object that has a variable in it. And if you give a value to that variable, then it becomes a proposition. Okay. So a predicate is something like this. P of X is a predicate if it becomes a proposition when X is replaced by a value. Okay. Now, for reasons that we will see later in this course, we have to say when X is replaced by a value in our universe. So we always need to have a universe. We have to say where these values come from. Okay, so let me give you an example. Let's say I say P of X is this statement. It's the statement that X squared is equal to 2. Okay. So you cannot really say that this is a proposition because you cannot assign truths to this. Is this sentence true or false? X squared is equal to 2. That doesn't make any sense unless you have already assigned a value to X, right? But then I can talk about P of 5. And P of 5 basically says that I'm replacing X with 5. So 5 squared is equal to 2. So P of 5 is false. It's always false. It's a contradiction, right? Or I can have P of square root of 2. And P of square root of 2 is actually true. It's always true because square root of 2 squared is 2. Okay. I can also take P of minus square root of 2. And this is also true. This one is false. This one is true. This one is true. Okay. But I have to have a universe. So if my universe is real numbers, I could assign any of these values to X because 5 square root 2 minus square root 2, they're all reals. But if my universe was the universe of integers, then I couldn't use square root 2. So I couldn't find any value that would make P of X to be true. Okay? But generally, that's what a predicate is. Predicate is just some sort of a parameterized proposition. When you give a value to the parameter, it becomes a proposition. Now, it doesn't have to be just one parameter. I can have several parameters. Okay, so instead of just having P of X, I can have something like P of X1, X2 to Xn, right? So I can have something like this. I can say P of XY is the statement X is greater than square root of Y. That's fine. And this statement will only become a proposition when I give a value to both X and Y. Without that, it doesn't have much of a meaning. Okay. Well, I mean, it does have meaning. It doesn't have a truth value. It's not true. Okay. So based on this, we want to now define some new operators in our logic. We want to be able to do new things. So, and these are what we call quantifiers. The first quantifier is the universal quantifier. And the way we write it is a bit weird. It's like this, an upside down A. and we read it for all. So I can write something like this: for all x, p of x. What this means is that I'm claiming, or I'm promising, that for every x in my universe, p of x holds. Okay. Now, I also have the dual, which is the existential quantifier. And we write it like this. It's a backward E. So if I write something like this, it means that there exists at least one x such that p of x is true, such that p of x holds. It doesn't say that there exists exactly one x. It says that there exists at least one x. Okay. And this x should, of course, be in my universe. So whenever I'm doing these quantifiers, whenever I'm using these quantifiers, I'm quantifying over my universe. So that's why it's really important to know whenever you're doing mathematics, what is your universe? What is the set that you can use to give values to these parameters here? Okay. So now I can use these quantifiers to also write new statements or new propositions. So for example, I can write something like this. I can say for all x, x squared is greater than 0. Okay. So x squared greater than 0 on its own is a predicate. But when I put for all x before it, this whole expression would be a statement. Because now I can assign truths to this. I can say whether it's true or false. I'm saying that for every element x in my universe, x squared is greater than 0. Okay. But is it true or false? Well, it depends on what my universe is, right? If my universe is the universe of real numbers, then, well, it's false because it says greater than 0. I have to say greater than or equal to 0. Okay, so if my universe is the universe of real numbers, then this is true. But if my universe is the, let's say, the set C, so I'm considering complex numbers, then I can have stuff that have a negative square. So I itself, I squared is -1, right? So this is now a meaningful statement. I can assign a truth value to it, but the truth value that I assign to it is very much dependent on my universe. So I should always know what my universe is. Okay, so sometimes to make this more specific, I can just write my universe here. So I can say for every x in R, x squared is greater than or equal to 0. But if I'm always talking about R, I wouldn't bother writing it all the time. Okay. Nice. So now let's see some more proof rules, or, well, another thing I can go back here is that we proved this theorem, right? But as soon as I prove a theorem, I can use it as a proof rule for proving other things, right? So I can already have this. I know that using these premises, I could prove this one. So new proof rule that you can use from now on is that whenever you have these premises, P implies R, not P implies Q, and Q implies S, you can immediately say not R implies S. And this is basically using this theorem as a lemma. Okay. First of all, let's find some equivalences. What happens if I have for all x P of x and I take its negation? What is this negation equivalent? So what does for all x P of x mean? It means that for every x that I can choose in my universe, P of x holds. So when I'm negating the whole thing, it means that it is not the case that for every x, P of x holds. So that means there should exist at least one x for which P of x does not hold. So this is exists x not P of X. Right? And of course, I can do the opposite as well. If I take the negation of exists X P of X, this negation would be for all X not P of X. Okay, let's do some rules and just give me the intuition for why these rules should be correct. So first of all, let's say that I have proven that for all X, P of X and Q of X. Okay, then I would say that this is actually equivalent to for all X P of X and for all X Q of X. Oh, I mean, it makes perfect sense. Intuitively, I'm saying that for every X in my universe, both P of X and Q of X hold. So I can say each part separately. I can say that for every X in my universe, P of X holds, and for every X in my universe, Q of X holds. Okay. Another thing I can do here is this. Let's say I say there exists an X such that P of X or Q of X. I say that this is equivalent to there exists an X P of X or there exists an X Q of X. Why is this the case? Again, I'm just going to give you the intuition. Basically, the idea is that I have one X. I'm promising that I have one X in my universe that satisfies P of X or Q of X. And it satisfies this if it satisfies at least one of them. Okay, so this X, this particular X, let's call it X0, that satisfies P of X0 or Q of X0, it should satisfy one of them. So either I have the same X0 satisfying P, or I have the same X0 satisfying Q. So in any case, I will have one of these. And you can do it in the opposite direction as well. Okay. But now, here are the interesting parts, the logical fallacies, what you see in debates by people who don't understand mathematics. Can we do this? There exists an X, P of X and Q of X. Is this equivalent to there exists an X P of X and there exists an X Q of X? No, this is not equivalent. Because this first one on the left is saying that there is some element X in my universe, and this same element at the same time satisfies both P and Q. But the one on the right is saying that there is some element that satisfies P, and there is some probably other elements that satisfies Q. These are not the same. Okay. Let's give a simple example of this. Let's say that my universe is real numbers again. And let's say I say P of X is greater than 0, and Q of X is less than 0. Okay. And then on this side, I will have that there exists an X that is greater than 0, and there exists an X that is less than 0. Now, these two are not equivalent. The one on the left is false when it comes to real numbers, because you don't have any value of X that is both positive and negative, right? But the one on the right is true for real numbers, because of course you have at least one positive number and at least one negative number. So you cannot do this. And similarly, when it comes to the universal quantifier, you cannot do it with OR, right? So if I say, change the color. If I have for all X, P of X or Q of X, this is not equivalent to for all X, P of X, and for all x q of x. Okay, and it's exactly the same reason as before. It's that these two x's can be different, right? So actually, in this case, the one on the right is having a stronger requirement. So the one on the right is saying that for every x that I did, oh, this was supposed to be or, not at. I mean, of course, it's not equivalent to this one either, but yeah, I didn't mean to write it like that. This is or. Okay. So here's the thing. Again, I give the same example so that you see what happens. Let's say that our universe is the real numbers R. I can say for every x, x is greater than or equal to 0, or x is less than 0, right? But it's not the case that for all x, x is greater than or equal to 0, or for all x, x is less than 0. So they're not equivalent. You see, this one is saying that every real number is greater than or equal to 0, or every real number is less than 0. Both of these are false, so their or is also false. But on this side, it's saying for every particular real number x, this particular x is greater than or equal to 0 or less than 0. And this is true. Every x satisfies this, so this whole thing is. Okay. So be careful about these things. These are actually the most common problems in the exams. And again, you might not see these logical fallacies easily because in the exam, when you're writing a proof, you're writing it in English. But you have to always think of it in terms of the formal mathematical statement that you're saying. Okay. So generally, we have a rule that if you have any kind of logical fallacy in any of your proofs, you get 0. It doesn't matter if the rest of the proof is correct. Okay. So we can have more rules like this. I will give you something to read about how to have even more logical rules and rules of inference with quantifiers. But I don't want to do that anymore. I want to switch to the next topic. Oh, and generally, this is how this course is going to be. I will give you the main important things that you have to learn, and then I give you a lot of reading and watching. So you have to watch a lot of YouTube videos and read a lot of books. Let's get to the last thing that we want to do today, and that's defining what natural numbers are. Now, up until this point, we were just using all sorts of things as our universe, and we didn't really care. I was saying, oh, let's say the universe is the set of real numbers. And I was just assuming that we all have the same understanding of what real numbers are, right? But I haven't defined real numbers. And at some point in this course, again, I will do that. But before I do that, I need to define natural numbers. So what are the natural numbers? Now, if you open a high school textbook, you might get something like this. You might see that the set of natural numbers is defined like this: 0, 1, 2. Sometimes they don't have the 0, 3, whatever. Okay. Now, this is not a good definition. From the point of view of a mathematician, this is very vague. So what do those dots mean? Is it going to end at some point? What are exactly the elements of this set? If someone gives me some element, how can I check that it's actually in this set or not? So we're going to have some rules for saying what's an integer. Or, well, sorry, in this case, for saying what's a natural number. And then, of course, we can add negative numbers and then define integers. Okay, so these are called Peano's axioms. So here are the axioms. Okay. Axiom number 1, 0 is a natural number. This is easy. Now, he has 4 other axioms that people usually don't mention. I'm going to mention them, and then I'm going to erase them because they're kind of stupid. But they were there when he first defined these things. So axiom number 2 is that for every natural number x, x is equal to x. For every natural number x, x is equal to x. Now, why do we need this? Because he lived at a time where people had not yet formally defined equality. So he had to actually invent the wheel and even define equality. But later on in this course, when we're doing set theory, we have definitions of equality and we just use that. So I will erase this after a while, but let me just show you some other things that he said for equality. It's like historical and interesting. So it says that for every 2 natural numbers, x and y, so for all x and y that are natural numbers, if x is equal to y, then y is equal to x. Okay. The next one is that for every x, y, and z that are natural numbers, if x is equal to y and y is equal to z, then x is equal to z. Okay. And also, this is another one which is very weird. It says that for every object B and natural number A, if A is equal to B, then B is also a natural number. Okay. So these parts of the axioms, again, these are just historical. We don't need them anymore because we know that mathematics has progressed a lot. And we know what equality is. Again, at some point in this course, we will also question that, but not for now. Okay, let's actually write the axioms that matter. So the second axiom, assuming that we don't have the axioms of equality, or assuming that we don't need to say the axioms of equality, is that every natural number has a next number or a successor. So every natural number n has a next number or a successor. And we show that by S of n, the successor. Okay. This is the second one. The next rule is that if I have 2 natural numbers and their successors are equal, then those 2 numbers are also equal. Okay. So I write it like this. I say, let's write it completely. For all natural numbers n and m, if the successor of n is basically n plus 1. But the reason I'm saying successor of n is that I haven't defined addition yet. At this point, I don't have access to addition. I'm just defining the numbers themselves, right? So if successor of n is equal to the successor of m, then n itself is equal to m. Basically, successor is a one-to-one function. That's what that means. But again, we haven't defined functions yet, so we will define that at some point. Now, we need one more axiom. Well, actually, we need 2 more axioms, but the next one is kind of surprising. That's so here's the thing. When we are axiomatizing something, when we are writing a bunch of axioms, we want to have as few axioms as possible. So anything that I can get as a theorem by using these axioms should not be another axiom. There's no point in having extra axioms, right? So it's always surprising that this one is an axiom. Axiom number 4. For all natural numbers n, the successor of n is not 0. Okay. Now, the last one is the one that we're going to talk about for several sessions, and this is called the axiom of induction. It says this. It basically says that, well, look, I have some way of creating some natural numbers. I know that 0 is a natural number. I know that then I can take the successor of 0. So the successor of 0 will also be a natural number. Of course, in human language, we call that 1. And then the successor of 0 will also be a natural number, which we call 2, and so on. Okay? But now I want to say that these are the only natural numbers. So if I just keep taking successors, so if I start at 0 and I just keep looking at successor of 0, successor of 0, and so on, this will give me all the natural numbers. Okay? So this is how we write it. We say that if K is a set such that 0 is in K, okay, and for every natural number n, if n is K, then n plus 1 is also in K. Oh, I cannot write n plus 1, sorry. S of n is also in K. Then K is the same as the set of natural numbers. So basically all it's saying is that the only way you can create natural numbers is using the previous rules. You don't have anything other than what you have created using the previous rules. So if you have any set K and you have 0 in it, and whenever you have some number n in the set, you also have the successor of n in that set, then your set is equal to the set of natural numbers. And this is big K, this is not small k. So when I'm writing, it's sometimes not very obvious. Okay, because it's a set. Okay, great. These are Peano's axioms. And basically, this is the definition that we have for natural numbers. So whenever we talk of natural numbers, this is what we mean. Okay, but this last rule, it's a very interesting rule, because this is the basis of all mathematical induction. So suppose that I want to prove something about the set of all natural numbers. Okay, so suppose that, for example, I want to prove this. Let's say I want to prove that all natural numbers have some particular property for all n in n, p of n holds. Okay, so for example, maybe I want to prove that for every n in n is greater than or equal to 0. Now, at this point, I haven't defined greater than or equal, but please excuse me for that. Let's just assume that I know what greater than or equal means. Okay, great. So if I want to prove such a statement, one way of proving it is by using this last axiom of Peano. So I can say, consider the set of all the numbers that satisfy my predicate P. Okay, so I can say something like this. I can say, let K be the set of all natural numbers such that, or natural numbers n, such that P of n. Okay. Now, I want to prove that for every n in n, P of n holds. So what I want to prove is that K is equal to n. I want to prove that this set K is the same as the set of all the natural numbers. But I can do it using this axiom. So all I need to do is to show that 0 is in K, and whenever some natural number n is in K, then the successor of n is also in K. So basically, I need to show two things. Or I can write it like this. It is sufficient to show two things. First, I want to show that 0 is in K, which is the same as saying that P of 0 holds. Okay, P of 0 is true. And then the second thing that I want to show is that for every natural number n, if P of n holds, then P of n plus 1 also holds. Right. So P of 0 holds is the same as saying 0 is in the set K, because that's the definition of K. I said K is the set of all natural numbers that satisfy P. So this is the same as this part. And this one is the same as the second part. I'm saying that for every other natural number, if P of n holds, then P of n plus 1. Now, I hope you have seen induction before. So this is a very easy, intuitive thing to do. I want to show that this particular property holds for all the natural numbers. I say, well, it holds for 0. And I show you that whenever it holds for n, it also holds for n plus 1. So intuitively, because it holds for 0, it will hold for 1. Now, because it holds for 1, I put n equal to 1, it holds for 2. Because it holds for 2, it holds for 3, and so on. And so it holds for all the natural numbers. That's all of what we're saying here. It's very intuitive, actually. But it comes from this axiom. Okay. And without this axiom, we cannot have it. Because, look, when we were defining our natural numbers, the role of this axiom number 5 was to say that the previous axioms give us all the possible natural numbers. If we didn't have this axiom number 5, it would have been possible that we had some other natural number that was not generated using this process. And then for that particular natural number, I couldn't use induction to show that P holds. Anyway. So this is how we get induction. Let me give you a preview of the next session because we're out of time. We're going to see two other ways of writing this axiom number 5. So we're going to see two, let's say, alternatives or two equivalent ways of writing this axiom. One of them is called well ordering. And well ordering says that every subset, every non-empty subset of n has a smallest element. It has a min. So again, this is something that makes intuitive sense. If you have a bunch of natural numbers and all of them are, of course, greater than or equal to 0, and if you take a non-empty set, you expect that there should be a minimum, right? So that's called the well ordering property. And in the next session, we will actually prove that it's equivalent to the axiom of induction. So instead of the axiom of induction, I could just put that. And I would get the same set. The other equivalent formulation of this is something called the axiom of infinite descent, or actually the impossibility of infinite descent, which basically says that you cannot have an infinite sequence of natural numbers such that each one of them is smaller than the previous one. Because at some point you will reach 0, of course, that's the intuition. But in the next session, we're going to prove that this is also equivalent to induction.